Yes, you are.
Okay, can I go ahead?
Yes, your screen is also visible, and please go ahead. Thank
Yeah. Hello, everyone. Very good afternoon. Thank you so much for this opportunity to express our research from our research group, what we are doing, how we are performing calculations using deMon 2K to support the electrochemical experimental results. In particular, we are using deMon 2K to model the carbon-based electrodes for supporting our electrochemical sensing results. So in this talk, Mhm. I will give a very small introduction about why we have selected graphene system for modeling. Then I will explain the methodology here by keeping in the mind of young PhD researchers who want to use D1 2K for their calculation. I will show one example how we can calculate uh, uh, analytical Fukui functions from daemon 2K, and then I will go with the results like we have used daemon 2K to model graphene system, in particular with defects like Stonewall's defect, double vacancy defect, doped graphene system, how we can know the reactivity, redox reactivity for electrochemical applications, and then we have also synthesized different functionalized graphene like cytosine and adenine functionalized graphene surfaces and surfactant immobilized carbon surface for sensing applications. So before beginning the talk, I would like to give very small introduction about the graphene. So, graphene, according to the IUPAC definition, we can say it's nothing but a single layer of the graphite structure. So, it's some constituents of the polycyclic hydrocarbons. So why this graphene is very much, why we are all very interested about graphene for electrochemical applications, because graphene has a very large surface area which will help us to improve the sensitivity of the electrode. And it is very much stable for a wide variety of temperature. Of course, the size of the graphene it's very thinnest as a, so the if you use it for any electrochemical application, it will become less weight. So it's a very good conductor of heat and electricity. So where we can use graphene for variety of application like solar cells to transparent electrodes, fuel cells, and electrochemical sensors. In particular, we are more interested in electrochemical sensors. Though graphene has these many applications and advantages, it has some disadvantage. Like it is quite toxic, and there are large number of research papers we will get on the applications of graphene, but very less number of, when compared to the applications, very less number of research articles available on basic research. And in particular, we don't know like how we can tune the graphene surface for electrochemical sensing application, and how we can reproduce the results. So for theoretical chemistry, for electrochemical modeling, we mainly use Fukui functions and frontier molecular orbitals. For those who are interested to know about frontier molecular orbital, they can read the first two references I have mentioned here, which was the articles of Kenichi Fukui, who he's a Nobel laureate. Like one can read this paper and get idea about how the frontier molecular orbital theory was developed. And then, like if you want to know about Fukui function, how Fukui function, developed by R.G. Park research group from 1984 by conceptual density functional theory. They can read the papers from 4 to 5. So in particular, we are using analytical Fukui functions, which for based on ADPT calculations in the deMon 2K software. So they can read like 6 to 8 reference from articles by Professor Roberto Flores Moreno. He is my PhD research guide. So, in a simple way, we can define Fukui function as a derivative of the total electron density with respect to the uh, number of electrons at a constant external potential. So, like, mm, so to understand why we need to club frontier molecular orbital like HOMO-LUMO orbitals and Fukui function, because if we use frontier molecular orbitals, it is something like we are observing or we are predicting the electron transfer reaction before the electron transfer process. If we are seeing, if we use Fukui function, it will give the electron transfer predicting or redox electrochemical transfer sites after the electron transfer process. We can simply imagine like we have a simple graphene surface. Here all carbon atoms are arranged in a hexagonal arrangement like a pristine graphene. It is something like if you give a cake to a small kid, you don't know where he will eat, right? So if you just close your eyes for 5 minutes, eat all the part, because all whole cake portion has a equal probability he may consume. So this is like when we perform homo orbitals of the Fukui homo orbitals by deMon 2K or any other software, we will get like this probability, because here all the carbon atoms have equal probability to lose an electron. But then if we perform Fukui function, what happens here also we will get the equal probability to lose the electron. Why? Because all carbon atoms are present in the same positions. So now if you think like if you give a boy cake with a cream, what happens? We guess most probably he will eat the cream portion. So like this is like some graphene surface with surfactant. Here we can see like homo orbitals are located on the pyridine ring of the surfactant. And then if we see the Fukui results, here also we can see like maximum electron transfer change occur at the pyridine ring of the surfactant. Why it is useful? Because when we perform electrochemical experiments, we don't know like from which portion of the electrode exactly electron transfer reaction occur. This quite may look easy, but if you think about, we have like a two functional groups in the in the any carbon system. We don't know which portion of the carbon is particularly active for redox reaction or oxidation or reduction. Here we can see simple carbon system. Here it is doped by the hexagonal boron nitride. As you can see here in the HPN system, we can clearly see like uh, when compared to the nitrogen, carbon and boron are more reactive for the electron donating, and nitrogen is not that much. That means here if we use like especially these kind of theoretical calculations will be very much useful uh, if we use like different catalyst material on the electrode surface to support the theoretical experimental result. Now imagine like if we have a uh, graphene or carbon system with some catalyst where many functional groups are present. We don't know when we perform the experiment which particular functional group is more effective for the oxidation or reduction or for the redox reaction. So these things I will discuss in the upcoming slides. So for almost all our papers, we have used Synapsys software, which is developed by my guide, Professor Roberto Flores Moreno in Jalisco, University de Guadalajara. And for finding, energy minima, we are using deMon 2K. In particular, we are using VWN functional with DCVP basis set for energy optimization. And once after optimizing the energy, we are using PVE functional with the TCVP basis set for Fukui calculations. So how we can calculate uh, Fukui function from deMon to K, it's quite very easy if one have a knowledge on Linux, terminal and Vim. It is very easy to perform deMon to K calculation. So for to perform calculation, first we will do energy optimization. Like here I have given simple example like water molecule. So here first line says that to the code like we need to optimize the molecule, and second line we usually we can mention basis set, or even if we want we can mention what type of functional we want. So and then here we need to give like a geometry Cartesian or geometry Z matrix to mention what kind of the geometry we have in the given input file. Then just type daemon minus op space dot x dot hint. Here in this case it may be water dot int. Like if we want to know at the beginning of the calculation only like whether the we have a we found the exact ground state energy, we can give something like frequency. If we want to calculate Fukui, we can give the keyword like Fukui. So once after the optimization, you will get like some other files like .mol, .mem, and .out. .out is very important. Like here, once you this simple example for the water molecule, like how we will get the output. So once after getting the output structure, so we usually won't optimize it again, and we will in particular we will give like print Fukui most and Fukui keywords to calculate the Fukui function, and then usually you will get results like this. This is condensed Fukui results. So then, like if you use the Synapses software, we can uh, plot the frontier molecular orbitals. Just open like in terminal type Synapses water dot out or any output you file and mention daemon 2K. You will get a file like this, and then you can select the whether you want to use the molecular orbital. Here in the water case, you select the HOMO or LUMO, and then just keep the plot. You will get the HOMO LUMO orbitals. And if you want to calculate Fukui function, what you need to do, you just need to go for plot manager and use the scalar. And then like if you want like Fukui negative or Fukui positive, you just like Fukui left or Fukui right, and you will get the Fukui plots. Like, so when I started my PhD, we start to understand the electrode performance. First, we thought to model the graphene. So when we tried to model the graphene, we were quite unsure like how many hexagons we need to select, and how what should be the size of the graphene system. This was a result even I have presented in 2013 deMon 2K 13th meeting in Las Cabos. So we selected like different model like carbon with the 24 number of carbon atoms, 54 carbon atoms, and 96 carbon atoms. And then so what we thought like let us try to see like if defects occurs in this graphene, how its electron transfer, redox electron transfer reactivity will change. In particular, we have selected like Stonewall's defect and double vacancy defect. In Stonewall's defect, what happens like two carbon atoms which will rotate in 90-degree. As a result, what happens? Four hexagons will become two heptagons and two pentagons. In double vacancy defect, usually it happens when two carbon atoms were misplaced from their lattice points. As a result, we will get an one octagon and two pentagons. Like to select the model, first what we did, we analyzed the carbon-carbon bond length, whether it will really matching with the experimental graphene results. When we try to model, like usually at C96, we have comparatively constant bond lengths. And then we have also studied Hertzfeld charges. Like if you see real graphene system, technically the carbon atoms should have a zero charge. Like again here C96 will show for almost all carbon atoms like zero Hertzfeld charge. Then we plotted once after selecting the model, we have plotted frontier molecular orbitals. Again, as I said in the earlier slide, like here all carbon atoms have an equal probability to donate or uh, remove the electron. That means homo orbitals or LUMO orbitals, all carbon atoms have a equal probabilities. Then we try to plot like Fukui negative and Fukui positive. Again, the post electron transfer process here also we are getting like all carbon atoms have a equal probability to remove or accept the electron. While it got very interesting for us, like when the Stonewall's defects occurs, what happens like in particular the carbon atoms which were rotated in 90 degrees, there the LUMO or atoms are LUMO orbitals are located and HOMO orbitals located in these positions. Like once after confirming the HOMO LUMO results, we have done the Fukui calculation. Here in this Fukui iso color density plot, here reactivity changes from increases from blue to red. So here also we are getting almost same results like the HOMO and LUMO orbitals. If it is confusing, like we also try to plot instead of Fukui colored isodensity, we have plotted the Fukui isosurface results. These results are matching with the frontier molecular orbitals. So we confirm our results like this, and then we done the similar calculations for the double vacancy defect. Here we can see like what we want to say, like even by the due to the formation of defects, again the carbon surface reactivity will change. Why it is very important when we perform any electrochemical experiments, like if defects will form, the reactivity will change. As a result, we will get the different type of sensing applications. Then we to test our results, we selected some simple conducted some simple cyclic voltammetric experiment. Here, BCP means just like a bare carbon surface, and FMCP means here we are attaching ferrocene to the carbon surface. When we perform experiments, what we observed, like at bare carbon phase, we haven't seen any electron transfer peaks, like for but once after the addition of ferrocene, what happens? We are able to observe both redox peak, like oxidation and reduction. To support these results, like we perform calculation in deMon 2K. Like first, what we observed, like when we modify the carbon system from the ferrocene, how the ferrocene may interact with the carbon surface. We find at FMCPC configuration lowest energy. Therefore, we are guessing that when we perform the experiments, most probably ferrocene likely to absorb on the carbon surface in this way. Then what we did, we uh, we performed the Fukui calculation. Here we can see like uh, uh, when we perform the Fukui calculation, if there is only carbon system, almost all carbon atoms are equal probable to remove the electron. But in presence of ferrocene atom, what happens? Like the electron will be mainly removed from the iron atom or from the ferrocene molecule. So this supports the experimental result. Like we saw oxidation peak in presence of the ferrocene. So here our Fukui results are telling exactly same thing. Similarly, when we perform the for the reduction, like see here we can go see the LUMO orbitals of the carbon. Again here all carbon have a equal probability, but when we see in presence of ferrocene or iron molecule in the +1 state, like here iron is the most probability to get the electron. Then we perform again we extended our model to analyze boron and nitrogen doped carbon system. Here also we publish this in New Journal of Chemistry. So here also we can see like for the if F minus, like if we present from the boron and carbon atoms, easy to remove the electron. Again, to add the electron, nitrogen will be preferred because of their electronegativity. And then what we try to do, we further try to extend or to interrelate electrochemistry results and Fukui results. what we did, we functionalized the graphene from the different type of organic molecules. Here we have selected cytosine and adenine. Here, if you see, like this is just carbon system, normal graphene. We can imagine like this. This is just the graphene. We have when we just use the graphene, we get the redox peak current like this. But when we add the cytosine, like red color, and when we add the adenine, we can get the peaks like here mentioned in the green curve. So what it indicates, when we perform the experiment, if we add a different organic molecule, we are getting different currents. Why it is occurring like this? Then again we have used the deMon 2K to calculate the global electron transfer properties. Here we can see, like at cytosine we have more higher electron donating and accepting power when compared to adenine. Like therefore, we are getting at the adenine, we have the higher electron donating power. So therefore, we are getting the higher redox currents when we perform the experiments. And then we have again used to understand if we have like cytosine or adenine, from where the redox electron transfer reaction may occurs when we perform the experiment. Again, here also frontier molecular orbitals and Fukui results are matching. And then we further extend our model to surfactant immobilization. Here we selected surfactant, mainly benzethonium chloride. So here we can first be predicted using deMon 2K, like how the surfactant may absorb on the graphene surface. And then we find the energy minima structure, and then we plotted the homolumo orbitals. So they are located on the phenyl rings of the surfactant. Here, these results exactly matching with the Fukui. So then we have applied it to for some practical application, like detect dopamine in the injection sample, and we found very good results. And then we further extend the model once after getting success to analyze some other surfactant like cetyl pyridinum bromide. Again, we followed the same procedure, and then we found, like by Fukui, like we can see, like uh, um, since it's a cationic surfactant in the phenyl ring, in the pyridinum ring, you can see usually this portion will get the electron because of the cationic nature. And again, already it is cationic, but again it is very difficult to remove electron from here. So then we applied it to detection of the uric acid, and we got a good result. At this time, we got the comments from the reviewer. Instead of making like two plots for Fukui function, you can do the dual Fukui. Again, using deMon 2K, we have started to compute dual Fukui function. We got results exactly same like the when we perform the Fukui function. So then we applied it to detection, for the detection of ascorbic acid. Again, we got very good result. We are able to publish again this in the Journal of Molecular Liquids. And at the end, I would like to conclude that if we combine analytical Fukui function and cyclic voltammetry, we can understand what is occurring at the electrode interface very easily. If we use deMon 2K and Synapsys software, like Synapsys mainly to plot the deMon 2K results, we can easily understand many conceptual density functional theory parameters. So it is very useful for experimentalists to gain more physical meaning or understand in the molecular level what is occurring at the electrode surface. And in particularly, I like about deMon 2K, we have published more than 50 research articles from deMon 2K, because it's very user friendly, and you don't need to pay if you are using it for the academic purpose, and you will get results very faster and very simple to analyze. Yeah, I'm very thankful to 23rd deMon 2K developer workshop organizers to for allowing us to share our results, and I'm also thankful to my management and the administrator for providing workspace. Thank you so much. Thank you.
Are there any questions from the online speakers or from the offline participants? Yeah.
Hello, very nice presentation.
Thank you.
Myself Pragya. I want to ask few questions. It may
Uh-huh.
be very stupid also. It's like
No, no.
you have used functional PBE.
Yeah.
Uh, could you explain me the point of taking PBE functional here? Because as I see, it is
Uh-huh.
a graphene and the surfactant is also like doesn't have any metal atom as such. So
Uh-huh.
generally it is said that if you have a organic background like carbon, hydrogen, oxygen, nitrogen, it is good
Uh-huh.
to go with B3 leak unless and
Yeah,
until you have a
obviously, if
transition metal.
yeah, I completely agree with you. Like in D1 2K, we can use BLYP. I think B3 lip is not possible. In fact, we perform many calculation with BLYP. Obviously, we will get a good results. But again, here the cost of computational time is very important because if we use BLYP, again it will consume. We have like more than 200 atoms. It is very difficult to run this calculation if we don't have anything like a cluster facility or computing. Like it is preferable to use BLYP. It will be results will be more accurate. That's why I'm not talking about the energy. I'm talking about only local electron transfer properties.
Okay. And the second thing, have you considered the dispersion effects on the calculations?
Yeah, when I perform deMon 2K calculation, I haven't considered like when we run same calculation in some other ports like WASP or other, we are considering. To be frank, I don't know how to use these dispersion things like D3 calculation in deMon 2K. It will be in deMon 2K we haven't considered. In when we run calculation in other software, we are considering.
We have discussed directions in.
Yeah, I
Thank
don't
you.
know. Yeah. Hmm.
Thank you, Pragya, and thank you, Dr. Gurraj. Itzonka, you have some questions?
I have a question. Thank you. It's very interesting to see, and also I really enjoy your beautiful presentation with the graphical presentation of the Fukui
Thank you.
functions.
Thank you.
Uh, did you calculate also, because for the electrochemical application, it's very important that we know the band gap of the graphene. Did you try to compute it with deMon and to see how much is the band gap of the model you studied?
To be frank, I'm using deMon 2K only for molecular density,
Okay.
molecular DFT. We are not using deMon 2K for solid state DFT calculations.
Okay,
Uh,
okay. I
maybe,
see.
yeah,
But okay, so
yeah.
when you calculate it, but if you use the periodic, what was the band gap? Did you calculate it for even not with deMon 2K? I mean,
Yeah, like for graphene, we haven't calculate. We calculate like other 2D materials like germanium, arsenide, and other things. So we are mainly trying to explain local electron transfer properties rather than the global electron transfer properties. Maybe it will come results. We will try to consider it.
okay, okay. Thank you very
Yeah,
much.
yeah. Thank you.
If there are no other questions, let us please thank Dr. Gururaj for his presentation.
Thank you. Thank you.
The next presentation is by Ravi.